All right. So what we're interested in today is developing some kind of quantitative model for a situation. So, and the situation might be physical, might be economic, might be sociological, different kinds of situations, not necessarily all physics type things. So when we do this, we generally identify, we think about the things that are changing, so the variables, we want to know what the variables are. And then we want to know about the detail. What kind of detail do we want? So we might say we're ignoring friction. We might ignore the curvature of the Earth, etc. Those kinds of assumptions that we make. If we want a more accurate model, we might not ignore friction. We might not ignore air resistance. So then we make some conjectures, and we use information that we know, including mathematical laws, like Newton's laws, those kinds of things, any relationships that we might know, to try to come up with an equation. The models often have to do with rates of change, because that's one of the things that we measure, that we can figure out, is how quickly something is changing with respect to time, or with respect to distance, or whatever. So our models often involve differential equations, or systems of differential equations. And if we can solve these, then we decide if our solutions are accurate models of what we're interested in. And if not, then we figure out what modifications we need to make. So what I want to do is, this is section 1.3. Is just talk about a few very typical mathematical models, some pretty familiar. They come up frequently in application. Our book talks about these as well. The book goes into a little more detail, maybe with some examples of calculations. But basically, the idea of this section is to introduce a few of these mathematical models. So one, and we talked about this the other day. Radioactive decay. And this would also be population. Population growth. For radioactive decay or population growth, what we are saying, our assumption is that the rate of change is proportional to the amount that we have. Of whatever material. I'm just going to say the amount of blank at time t. So in words, this is our model. The rate of change of the population is proportional to how many people we have. The rate of change of the mass of the radioactive sample is proportional to how much there is. So the way we write that equation is dA dt, where a is a function of time, is some constant times a, where a is our amount. And a solution to this, you get exponential solutions to this differential equation. For growth, if our population is growing, K is positive. And for decay, radioactivity, or our population is decreasing, K is negative. So it's a very basic model of growth or decay. Another one, Newton's law of cooling. And this can also, we call it Newton's law of cooling, but it can also apply to temperature increasing. Newton's law of cooling, do you talk about that in physics at all?
Yeah, it got brought up in BC like
Right.
a little bit, but then it was like, oh, this won't be on the exam.
Newton's law of cooling says that the rate of change in temperature is proportional to the difference between the current temperature and the ambient temperature. So the way we would write that is the rate of change of the temperature with respect to time is some constant of proportionality, times T minus T, I'm going to say Tm, where T of T is our current temperature, and T sub m is the ambient temperature in the surrounding areas. So very similar model. This one ends up having exponential solutions as well, because really it's kind of the same thing here. And this applies if the ambient temperature is higher, then the thing's going to warm up. If the ambient temperature is cooler, it's going to cool down. When we did in pre-calc, do you remember the cooling corpse activity? Yeah, that's essentially that exponential model, essentially Newton's law of cooling, because the body was in the room that was at the room temperature, and it cooled down, and we had to figure out what time it reached extrapolate back to when it was at body temperature to figure out when the person was killed. Mixtures. This is the tanks with saline solution, etc. For that one, the rate of change, I'll write in words. Of the material in the mixture is the rate of inflow minus the rate of outflow. So rate in minus the rate out. So you have a tank, something's flowing, there's a concentration of the material in the tank, some other concentration flows in, some other concentration flows out. The rate of change of the amount is the amount. The rate of change of the amount flowing in minus the rate of change of the amount flowing out. The trick with these problems is to translate the information that they give you into these rates. Because they'll say the concentration is 10 pounds per gallon, and the rate that it flows in is 20 gallons per minute. So you have to translate that to how much of the stuff is flowing in per minute. That's usually the tricky part. But it's a relatively simple differential equation. Solution to these, we'll see when we start actually solving these things, is kind of a logistic thing, and it ends up having to do with an integral like we just did on the board. Another classic example is series circuits. Do you talk about circuits in physics? So the classic one is called an LRC circuit. I'm just going to write the equation here. The voltage at the inductor and that is L times the second derivative of the charge per unit time plus the voltage at the resistor and that is the resistance. This is the inductance. The resistance times the rate of change of the charge with respect to time plus the voltage at the capacitor so 1 over the capacitance times the charge is the total voltage. L is called the inductance. R is the resistance. And C is the capacitance. So this is a very typical differential equation that shows up in physics and engineering. The inductance is measured in henries. The resistance is in ohms. And the capacitance is in farads. Q is the charge. And if we draw a picture of these circuits, a lot of times you have a picture of them. They look like this.
Oh. It's just E sub t.
Yeah, this is just a voltage as a function of time.
Yeah.
And the current is I, is the rate of change of the charge with respect to time. This is our capacitor, this is our resistor, and this is our inductor. Inductors are coils. Capacitors are those two plates that build up charge, yes?
Are we gonna need to know like what that'll look like?
No,
Or do you sound so disappointed?
no, I mean, it's not hard, but it's not something, it's not the point of what we're doing is to remember all that stuff. Just, the point of, for what we're doing is, if you have a differential equation like this, eventually we'll know how to solve it. So the current rate of change of charge with respect to time, so this we could write as the current. We could write this as I, and this as the rate of change of I with respect to time, I prime. So if we didn't have a capacitor in the circuit, if we just had an LR circuit, we could write it as a first order differential equation in terms of current. So that's another typical, very typical differential equation that comes up in application, is in circuits. Now, one thing that's interesting about this differential equation, it's a second order differential equation, we'll see, not in the next chapter, but the chapter after that, when we talk about higher order differential equations. When you solve, the technique that we'll use to solve a differential equation like this involves complex numbers with the square root of -1. So solutions to differential equations sometimes turn out to involve complex numbers, but it's exponential functions with complex numbers. So we are going to use the relationship between exponential functions, complex numbers, and trig functions. So we end up getting trig functions and exponential functions that model the current in a circuit. So the circuit varies in time, but it also might decay in time because of the exponential function. So some interesting things happen in differential equations where we see the relationships between some things that we've talked about over the course of the years that kind of come together with this calculus, complex numbers, exponential functions, trig functions, comes together in a nice way. It'll also involve finding roots of polynomials. Yes. The P's and Q's, yes. There was one differential equations class that I took, the professor, when they got to this point, said, so you remember all that stuff you learned in high school about finding roots of polynomials? Yeah, I expect you to know that. That was his introduction to the lecture on solving these kinds of equations. So others, there are several other models that the book discusses. It talks about the spread of disease, where we say the rate of change is proportional to the product, the number of people that don't have it, interacting with the number of people that do have the disease. So you get a product there. There's some other models in there. Gravitation is another one. And those will come up. There's questions about a couple of those in the homework, so you'll need to refer back to those models in the book. But they ask you to make some additional assumptions. Well, let's say there's this thing happening. Given this situation, solve for this constant, that kind of thing. So other examples. Are on pages 23 to 28 in section 1.3. All right, so just before we finish, I want to kind of give us a big picture of where we're going. So we've talked already about, does the differential equation have a solution? So that's one thing we're interested in. Can we solve this thing? Are the solutions unique? Well, for certain kinds of differential equations, we saw conditions when that happens. We'll talk about that situation for other kinds of differential equations. What are the properties of the solutions? That's what we're going to talk about next in section 2.1. Before we start solving differential equations, we're going to talk about, well, if we don't know the solutions or we can't solve the differential equation, can we figure something out about the solutions? Can we do something to gain some information about the solutions, even if we can't solve them. That's where slope fields come in. And there's a couple of other things that we can do as well. What does a graphical representation tell us? So again, the slope fields. Sometimes we can graph an approximation of solution families, and figure out how the solution behaves in certain areas of that we're interested in. And then finally, we're going to start solving differential equations using analytical methods. And if we can't solve the equations, can we approximate the solution? That's one in chapter 2, we'll talk about Euler's method to approximate a solution at a point. So we call that a numerical approach, where you don't actually solve the differential equation, but you approximate the solutions. All right, so that's big picture where we're going over the next month-ish or so. Okay. The homework will say, given for Newton's law of cooling, if this thing happens, write the differential equation. If you have this additional thing happening, write the differential equation for that situation. If you have the law of gravitation, but solve for this constant. So they'll give you some information, and you solve for the constant of proportionality. So you're just kind of doing some things with those models. There are a couple of questions about the mixture problems. So the tank has this much salt in it, and it's this its inflow at this amount. Write the differential equation for that specific situation.
You should have given a shout out to Josh. He'll be watching this soon.
Yeah, Josh, you should come to class.